We're gonna give people just a little bit longer to get on in here, so just sit tight for a little bit. All right, let's go ahead and get started. All right. So to start things off, I would like to start off with a little bit of an introduction and then kind of talk about how I plan to teach the class, right? So first things first, right? So my name is Kitong Lu. You guys can call me Mr. Lu, Teacher Lu, anything like that. It's fine. I don't really mind. Uh, I'm going to be teaching your class for geometry. This is our geometry class. Um, so really going to be talking a lot about like the shapes, right? There's going to be some geometrical proofs as well as just working with a lot of diagrams, right? So I graduated with a math degree from the University of Texas at Austin. I currently work in pricing insurance, so a lot of math there. So for the actual book, so here is what the table of contents looks like. So we're going to start off by introducing a lot of notation. So we're going to talk about the terminology that we use, the way that we write things out, right? So that's going to be really important. That's going to be what we're going to spend a lot of time on today for. After that, we're going to talk about angles. We're going to talk about um, this section in angles is going to be very important for the remaining part of the book. Then we start talking about triangles, congruency, as well as similarity. But then in between that, we talk a little bit about what perimeter and area is. But this perimeter and area, this idea is nothing new. So we're really just kind of rehashing it a little bit. So then we finish up triangles by talking about right triangles as well as special parts of that triangle, right? So we're going to talk about everything there is about a triangle. And so once we're done with triangles, we're going to talk about more sides. We're going to talk about quadrilaterals. And once we're done with quadrilaterals, we're going to start talking about just regular polygons in general. After that, we move on into other topics. We move on into figures that are not polygons, right? We move on into circles, geometric inequalities here. There's something that we call power of a point. We'll talk much more about that at a later point. And then once we're done with 2 dimensions, we're going to start talking about 3 dimensions. 3-dimensional geometry. We're going to talk about curved surfaces. And then after that, we talk about how we can change things around, right? Then we move into analytics as well as trigonometry, just introducing what that is. And then at the very end, we're going to talk a little bit about, we're going to put everything together and then talk a little bit about how everything comes together. But so geometry is a class in which I really think you can, I think you can take this class without having to know much else, as long as you're like, familiar with the basic arithmetic as well as the concept of variables. I think as long as you have that much, that should be fine. Like you can take geometry at the same time as other classes, such as like algebra 1 or algebra 2. But yeah, so that is kind of what we're going to be looking at for this class. And as for today, we're really going to start things off with just what is notation and why is notation important. So to start things off, right? So let's think about why notation is important. In the process of the geometry, we're gonna in a lot of the questions that we're gonna be going over, there's going to be very long descriptions of a diagram. There's going to be lots of shapes, and in order to make sure that you have everything understood, in order to make sure that you understand exactly what everything there means, we need to have some sort of regular method to notate what we mean. Like, for example, are these lines parallel? Are they, like, how many points are there? What are these measures of angles or whatever? I know that we haven't necessarily talked about what parallel lines are or anything like that, but these concepts should be ones that you are all at least somewhat familiar with. So yeah, oh, and one more thing. If any of you have any questions, you guys can always feel free to ask me with the chat, or just go ahead and directly unmute and ask me that way. Either way works perfectly fine for me. I'm always looking at the chat, so let me know if you guys have any questions. And I'm going to uh, ask you all to help me out with questions a lot of times. Maybe not as much this class, because this class we're doing a lot more of just introduction to exactly what our notation is. But apart from all of that, especially towards later classes, such as like maybe next week, there's going to be a lot more of asking around questions, right? So when I do ask you a question, please, if you wouldn't mind, unmute and answer. But if you would rather use the chat, just let me know, so I know to expect it. Otherwise, if you're not there, or if you're like, I don't know, busy with something, and you don't answer, I'll know to just go ahead and skip to the next person. But if you are there, if like, just make sure, like, either do some sort of reaction to let me know that you're listening, to like that you're there for the question, and that you're just typing, because I know like sometimes people take a little bit to type. But yeah, so hopefully everyone's familiar with using reactions. Hopefully everyone's familiar with using the chat. So if you have any questions on any of that, just say so now. All right. So let's go ahead and get started. So the first thing is why we need those notations, right? So we talked about how we're going to have pretty complex diagrams at some point. Those complex diagrams mean we're going to need to have some way to notate it. And to start things off, we start with the very, very smallest. The smallest thing possible is simply just a point. A point has no dimensions. A point does not have a distance, does not have a length, does not have anything. It just has a single location. So what we start off with is we start off with a point, a single location in space, right? So the way we notate this point is we would call it a capital letter. So say, for example, point P, right? Now, say we, take this one point and we have a different point. Let's call this one point O. Okay. What we can do is you can connect these 2 points. And then once we have connected these 2 points, we now have a line segment PO. Now, line segment PO and line segment OP are the exact same. It's just one has the start at P and the end at O, while the other one has the start at O and the end at P. But it doesn't really matter where you start and where you end, because a line segment has exactly 2 endpoints, and a line segment has a set length, a set distance, right? The length right here is what we would call the length of PO. But how would we denote the length of PO instead? In order to talk about the length of PO, we just write it without this line up here. We just write PO alone. This refers to the length between the points P and O. So let's say, for example, your house is, I don't know, 5 miles. Okay, 5 miles is a little bit long. Let's say your house is 1 mile away from your nearest school. Then that would mean that the distance between your house, let's say your house is H and your school is S, then your distance HS right here is just going to be 1 mile, right? So that's the idea here. But what if, for example, we have, let's go back to A and B, right? So this right here is AB, line segment AB. Now you've noticed that I've said this very consistently. I've always said line segment. And the reason why is because a line is very different from a line segment. A line goes on infinitely in both ends. So this is actually why we call it a line segment, because a segment is a piece of something. In this case, a line segment is going to be a piece of this line. It's just this part of this entire line. A line goes on infinitely in both directions. So if we're going to talk about the line instead of just the segment, like right here, what we've written is we've written line segment AB. So this still refers to just this part of it. It doesn't refer to the infinite part of the line. So what if we wanted to talk about the infinity part of the line? What if we wanted to talk about the line that goes on in both directions? Then what we would do is we would add on these arrows. These arrows that we have here get added on right here. And now we are referring to line AB. But what if, say for example, we started at A and go towards B and go infinitely in the B direction, but there's nothing beyond A. This right here is what we call a ray. A ray is kind of like a line, except you have a starting point, which in this case is our A, which we call our origin. And then we go infinitely in a direction. In this case, that direction is towards B. This way, we would write it as AB with ray AB. Now, what you'll notice is I have it written as a single one-sided arrow instead of that two-sided arrow. That's very important because that shows that we start at A and go towards B. Now, another thing, AB like this is actually also the exact same thing as AC. AB and AC are the same because they have ray AB and ray AC are the exact same because they both start at A and they both go infinitely in the same direction. But what about our line? Yeah, let's start things off actually from the bottom. So Wei, can you give me two lines here that are the exact same thing, that are the exact same line? Wei?
What was the question?
Yeah, can you give me two of the same, can you give me two different names for the same line in this diagram right here?
AC and BC,
So why are line AC and line BC the same?
because like they're both like don't have like the arrows on it. I mean, they both have the arrows, so
They both
and they're
go on
like the same
infinitely, right?
length. Yeah.
Well, they're not necessarily the same length, but I do see what you mean, right? Like they all refer to this one line right here, right? So even though they AC and BC are separate parts of that line individually, like they're separate segments of that line, we're still gonna end up taking up this entire thing, right? So that's why we have that AC and BC are both gonna be referring to the same line here. Okay. Now, we talked about what a ray is. We talked about what a line is. And one of the big things that we need to make sure about when we talk about a line is like line AB refers to the same thing as line BA, right? The same exact thing as we said about line segments. AB and BA, line segment BA, these two both refer to the same thing as well. Because we have a start, we have an end for line segments. For lines, we have no end in either side. But Serena, what about for ray AB and ray BA? Is there a difference here? Yes. So what is the difference between AB and BA? Rays AB and BA.
One arrow goes one direction, the other goes the other.
Yeah, Serena's actually answering in the chat, so maybe you guys didn't see that. But right, so that's actually also exactly what Serena had mentioned, the direction, right? So one of them starts at A, goes towards B. The other one starts at B, goes towards A. So those are going in completely opposite directions, which means that we're looking at completely different things here, right? So that's why that causes a difference, okay? And lastly, there's a couple of other things that we want to make sure of. There's something that we call a midpoint, right? So a midpoint should be something that is fairly self-explanatory. The midpoint is simply just going to be the middle of 2 points. That means that the 2 parts, AM, the length of AM, actually, Milo, do you remember how to write the length of AM? How would we write that out? Milo, you there? AM with the line on top. So when you're saying with the line on top, you mean like this, or do you mean with arrows at the end? No arrows? Okay, so no arrows right here. This refers to line segment AM. So we're referring to the actual line segment. So we're not talking about the length this way, right? So this isn't the way that we refer to the length of AM. Okay. Does anyone know how we refer to the length of AM? Give me like a hand, like a raise hand or something, I guess. Okay, Isabella, how do we refer to the length of AM?
I'm not sure, but I think it's AM equals BM.
You said equals EF? Did you say equals EF there?
No, I said AM equals BM.
Oh, BM. Okay. So that means what you're referring to is like nothing above A and M, right? Okay. So I was just referring to for this part, I was just referring to the length of AM, right? So I wasn't referring to anything else yet, but that is going to be actually correct. So AM alone with nothing above it, no lines, no arrows, nothing like that, right? If we have a line with one arrow, that refers to an array. If we have a line with no arrows at all, that refers to a line segment. With 2 arrows, that refers to an actual full-on infinite line, right? But AM alone, just written like this refers to the length of A to M. So this here refers to the length of A to M, but we know that this length is equal to the length of B to M. So we write that here that AM is equal to BM if M is a midpoint. Okay, so that refers, that's what a midpoint is. Now, what if we have, say, for example, what if we wanted to write out what those, what if we wanted to label that on this diagram? Now, what we do is we introduce what are called tick marks. So tick marks are very important because tick marks give us information about the diagram. In this case, if we wanted to represent that AM is equal to BM, then what we do is we represent that with these tick marks like this. Now, tick marks can be in many different ways. If there's more than just a single pair of line segments that are equal in length, then what we can do is we can have a different kinds of tick marks. Say, for example, there's another line segment here that's the same length as this one. Let's call them, I don't know, XA and YB. Then what we could do here is we can mark it with 2 tick marks instead. So we can go on and go on and go on, right? We'll have 1, 2, 3, 4, like you can have however many you want. But normally you stop around 3 or 4 because at that point it starts to be a little bit hard to count every single tick mark on everywhere, and it just becomes hard to keep track of, right? Tick marks are supposed to help you. They're not supposed to make it harder to view, right? So this is how we convey information in that diagram. Now, all right. So those are what tick marks are. We've talked about midpoint. One more word is equidistant. Equidistant just means that a single point is equal distance away from 2 other points. Equidistance. Okay. This is just basically another word for midpoint. All right. And lastly, we need to talk about what it looks like when lines intersect. So when lines intersect, they will have a single point of contact, right? But what if more than two lines intersect all in the same spot? What if we have a third line, let's say right here? So let's say that these three lines all intersect at this point. I know I've drawn it a little bit off, but we'll say for the sake of the diagram, these three lines all intersect at the exact same spot. What we say is that these three lines are what we call concurrent. That means that all of these lines intersect at one same spot. Okay. And lastly, this is just a definition, right? And then one more definition that we have is collinear. So one of the things that we had mentioned was that 2 points make up a line, right? Now, if these 2 points make up a line, what if we introduce more points? We can introduce a third one if we really wanted to, right? So for these 3 points, right? These 3 points are all collinear because they all lie on the same line. But when we're naming this line, we only need to make use of 2 of the points. We do not need to make use of any more. For example, we can write BC, line BC. We can write line AB. We do not need to write line ABC. We don't need to do this. We only need 2 points to write that name. Okay, so when we are writing this out, again, we can pick any of these 2, 3 points. We can put them in any order we want. Every single time it will give us the same exact line, right? Because they're always on that same line. It doesn't matter which points we pick. It doesn't matter what order we put them in. All right. So now one final definition, and there's not a really good way to describe, to draw out this definition. So rather, we're going to talk about this, and hopefully you guys can imagine what this is. So our final definition is a plane. And what a plane is, Plane, what a plane is it is basically the area on which I am drawing all these diagrams. So think about, for me, it'll be my iPad that I'm drawing on. For you guys, it'll be the screen that you guys see me drawing on, right? So think about that plane. Now think about that, like that 2-dimensional flat surface, except it goes infinitely in all directions. So there's no depth to this. There's only length, which goes this way, and height, which goes this way. Length and width, I don't care. It only goes in these 2 directions, but it goes infinitely across all of these directions. It does not go in or out. It just has these 2 directions. It doesn't matter what you call them. You could call them length and width. You could call them height and width. It really doesn't matter, but only in these 2 directions, right? So this is what we call a plane. And you might wonder if there's only one such plane that could exist. Well, the answer is basically no, right? Like think about your room. Think about the walls in your room. Think about the ceiling, your floor, right? Most of you will probably have ceilings that are parallel to your floor, right? So that is if you extended the plane forever, these 2 planes would never intersect, right? Now, some of you might not have ceilings that intersect, that might have ceilings that are slanted or something. Well, unfortunate, I guess. But for the most part, you guys should have, for the most part, like you guys, like all of those walls in your room, like those will all be planes that like, and then you can see that in your corner of your room, right? Where those 2 planes intersect, think about where those 2 planes intersect. That's going to be a single corner of your room that goes straight up and down, right? That's the same thing as a line, right? And what that means is a plane is a 2-dimensional shape, right? It goes in both directions, right? It goes in this direction and this direction, right? While a line is simply just one direction. So if a plane and a plane intersect to create a line, then we can think about a line and a line intersect. Well, that should just bring down our dimensions by 1 again, right? We said that a plane is 2 dimensions, a line has 1 dimension, and a point has 0 dimensions. So that is part of the reason why when planes and planes intersect, you get a line. When lines and lines intersect, you get a point. And well, points and points don't really intersect, right? They really just overlap instead. But yeah, so that is the kind of idea that we really want to be going with there. So, any questions here? It's really just a bunch of definitions for the first like half of this. But yeah, if there's any questions, we can kind of talk about those. But otherwise, we'll go ahead and move onward. So next up, we introduce this idea now, but we're not really gonna explain. We're not really. We're not gonna explain. We're not gonna talk about it much further than this for a long while. So, there's a word that we like to use, which is locus. A locus is a group of points that satisfies some sort of condition. So let's talk about an example right now. So what if we started off with a point? Let's call this point O, okay? Around this point O, let's think about all of the points that are exactly, let's say, 1 inch away from O. Let's say 1 inch away from O. All of the points that are exactly 1 inch away from O. What would this collection of points create? Does let's go on. Josh, what is this collection of points usually called? Like, what's the normal name that you would call this? All the points 1 inch away from O.
What?
So if we took a collection of points, all of them are 1 inch away from another one, this one being O, what is that? What have I described?
A point.
So a single point maybe, yes, but I'm looking at all of the points that would be 1 inch away. What does that end up making?
A circle.
A circle, right? To be a little bit more exact, we create a circle with a radius of 1 inch. So a circle is one example of a locus. It's a group of points that are all the same distance away from another point, and that other point is the point in which we call the center of that circle, right? So let's say we have a circle. If we have this circle here, is it possible, Joseph, is it possible to draw a line still on my plane here? Is it possible to draw a line that does not hit the circle in any point?
I don't think it is.
So every line I draw has to go through this circle. Is that what you're saying?
Well, you could draw one off to the side.
Yeah, like this, right?
Yes.
And this line would never touch the circle. So this right here, yeah, this does not hit this circle anywhere, right? Okay, thank you. Now, Joanne, is it possible to draw a line that will only touch this circle at a single point?
I don't think so.
So this typically is what most people will think until they've learned geometry. Now, given that I've said that, what do you think the answer should be?
Yes.
Yeah, so the answer is yes. And we'll talk about this more eventually. We're not gonna go too much in detail about it today, but that line will look something like this. It will touch the circle at just this one point. And then after that, it never touches the circle again. Another example would be one that goes through right here, right? But what you may notice is that if you look at this and the radius, you might notice a little bit of a special relationship between that. But we don't really know, we haven't really learned any of that yet. So we're not gonna go too much in detail about it, but we call these lines tangent lines. A tangent line only touches a circle a single time, okay? And one more thing about notation, right? So we've mentioned that points will be written with capital letters, right? Capital A, capital B, these are all points, right? Now, what about lines? Now, normally we said we can write a line as, say, for example, line AB like this, but we can also do it by calling it a single lowercase letter. And usually that lowercase letter will be italicized. Now, italics is a little bit hard to write out. So I'll do my best, but usually I'm just gonna use like L, M, and say, for example, N like that. And then we'll go with those. But yeah, so lowercase letters italicized will also be a way that you can name a line. And do note that in this case, you do not need that line with the two arrows above it. We just need to write the lowercase letter italicized. We don't need anything else. All right. So it is possible to create a tangent line, a line that only touches the circle a single time. So moving on, Jared, is it possible to have a line that will touch that circle at least 2 times?
I think so.
Yeah, something like this, right? Goes straight through. Now, this right here, we have to kind of think about it a little bit, right? So I said at least. To be very exact, it's only possible to hit it up to 2 times. We cannot have a straight line go through this circle more than 2 times, because if we had to touch it another time, we would have to start curving this line, right? And that's not a line anymore. A line is straight. It goes in a straight direction in both directions, right? It goes in both straight directions, but it only goes straight. It never curves around, right? So that is what we're looking at there. Now, a couple of these lines have special names, right? We had talked about what the tangent was. It's the one that only touches that line a single time. Now, what if we have a line that goes through 2 parts of that circle? This is what we call a secant line. Okay. A line segment that goes through, that has the 2 endpoints on the circle. So 2 of my endpoints are on that circle, right? This is a line segment. It does not go infinitely in both directions. Tangent and secant both do. This right here is what we call a chord. Sorry. So a chord is going to be a part of a secant line, right? It's going to be a single segment of that secant line. Now, if this chord were to pass through the center of the circle, we would call this our diameter, right? A little bit out there, but yeah, so if it goes through the center of our circle, we call this a diameter. Now, the portion of the circle that connects through the circle, let's say, for example, this right here, this is what we call an arc. Our minor arc is going to be the shorter of the 2, right? This one is the shorter of the 2 different ways. We could have also gone this way around. This is what we would have called our major arc. Now, if we need to talk about our major arc, we're going to refer to it with 3 letters. So let's say, for example, we have a couple points on this circle. Let's say A, B, C. If we wanted to refer to arc BC, the short version here, we would write BC like this. But if we want to talk about the longer version, the one that goes all the way around, we could do BAC like that. So BAC is the one that goes all the way around over the back. BC is the one that goes straight to it. So these are the 2. This right here is the notation for our circles. Now, we're not going to need this for a long while, so just hold on to it. But if it comes to it, we'll just go ahead and review this when we do need it. But with that, are there any questions over any of the notation type stuff that we've talked about? Okay, so that's actually it for chapter 1 for the most part. There's a little bit more that I do want to talk about, but one of the things that I did want to go ahead and address is that in the course of this textbook that we're using, there's going to be some sections that refer to what are called constructions. However, constructions are a little bit tricky. Constructions, we have to use two things: a compass, so we can draw circles, and a straight edge, a ruler, but we're not supposed to use the ruler to measure, right? So the problem with this is it's a little bit hard to do that over Zoom. One thing is I can't really pull up a compass and ruler and show you how to use them. Another is that you most likely won't need to do constructions inside of actual school either. Like if you're taking geometry in high school, constructions are usually not something that is covered at all. So because of those reasons, I'm not going to cover constructions. I'm just going to skip through these sections when we do come up to them. So yeah, this is just stuff that I'm not going to teach because it's typically not taught in school either. All right. But with that actually brings us to the final section of this chapter, where we introduce not more notation, but rather we introduce a concept. This concept is what we call the burden of proof. The idea here is we need to think about what we need to do in order to prove something to be true. So one such idea, one good example is the Pythagorean theorem. This is something that most of you have probably used many times by now. The Pythagorean theorem simply states that a squared plus b squared is equal to c squared in a right triangle, right? Where a and b represent the lengths of the legs and c represents the length of the hypotenuse. I know I'm using a lot of words that we haven't talked about strictly within this class. So if anyone's not familiar with them, I'm sorry, but this is probably one in which you probably have worked with by now. So yeah, so we take these here, right? Now, why are you able to use this? Why are you able to use this theorem? The reason why you're able to use this theorem is because at some point, someone proved that this was true in all cases, right? So what we need to do is we need to prove everything we use in this class. We need to, and that's going to be a recurring kind of theme in this class. We're going to introduce something new. We're going to talk about exactly why that is true. And then from there, after we've mentioned why it's true, after we've proven it, we can start using it to prove other things, right? So, but everything needs to start from somewhere, right? We can't just, like, say, for example, we cannot, is there a way to prove that 2 points make a line, right? So that's the kind of idea behind the burden of proof. There are some things that we simply just cannot prove. It's just impossible to prove, right? The very first one that is impossible to prove is that 2 points make a line segment, right? And that if you extend that line segment, you create a line. There's no way for you to prove that. It's just impossible to straight up prove. There's no way to start and end with the proof. So because of that, there's some things in geometry that we just have to accept. And what we call these is we call these either axioms or postulates. Axioms or postulates. Okay, so these here, if we mention that, okay, this is an axiom or this is a postulate, that means that this is something that we cannot ever prove. There's no way, no one can prove this, right? Because it's either just so straightforward or so simple that there's no way to make it more simple, right? Like think about if you guys are familiar with elements versus compounds, right? Like once you make it that element, there's no way to go any further down than that. That's kind of what we're doing here. We're saying that this is as far down as we go. Once you get down to this is just something that we have to assume is true. Okay, so two of the ones that we've mentioned already, 2 points make a line segment. A line segment can be extended to create a line. There's a couple more. So there's 5 on this page here on section 1.5. But there's only maybe like 1 or 2 more that we would really talk about here. I'm not going to write these down because they're quite long. But if you're interested in them or want to review them, you guys can just read over this page on your own. But some of the others are that if we have a straight line and a point that is not on this line, there is going to be only one line that goes through this point here that does not intersect this one here. We have a special name for this that we're going to talk about in a future section. Another axiom is that all right angles are congruent. We haven't talked about exactly what either of those words mean, right or congruent, but we'll bring that up eventually. And a final one is that given any line segment, we can draw a circle that has one of the endpoints as a center. And then this circle will have this line segment's length as a radius. And I just realized that ended up being a lot worse than, it's passable, I guess. But yeah, okay. So these are what we call axioms. There's no way to prove these. It's just so simple that there's no possible way for it to prove it. However, if we start with given information and move from that given information by using step by step, this is something that we've proved before. This gives us new information. This is something that we've proved before. This gives us new information, right? If we do something like that, that is a step-by-step proof. And this step-by-step proof, until we're sure if it's true, until we're sure whether it's true or false, we call this a conjecture. And once we know whether it's true or false, at the end, it becomes a theorem if it is proven to be true in all cases. And that is why the Pythagorean theorem is called a theorem, because it has been proven to be true. But all right, so those 5 axioms that we had mentioned here today, those aren't all of them. There's going to be more, but we'll bring those up as we come across them. So does anyone have any questions on what this kind of talk was about? Like, we're really just explaining what the proof part of this class is going to be covering. How you move from step to step. You just need to go from what you know, what you've already known, to what information that gives you. But with that, and as always, if you are a little bit shy, feel free to just direct message the question to me. You guys can do that, and then if you do that, I'll have to read out the question so that everyone knows exactly what I'm answering, but no one will know who asked it. But all right, with that, that's actually the end of chapter 1. And with that, we'll start talking about chapter 2. So chapter 2 introduces a new concept to us. Now, one of the things that we had talked about in chapter 1 was what a ray was. A ray starts from one point and goes on infinitely in another. For example, let's say we have A to B here. But what if we had another ray that also started from A and goes in, let's say, this direction? If this, let's say, point C, now we have 2 rays. We have ray AB and we have ray AC, right? These 2 rays start at the same origin. They share this common origin A, right? This angle that is created right here, we call this angle CAB or angle BAC. These two both refer to the same angle. We can also refer to this as just angle A alone, if it's pretty obvious what we're referring to. But what you may have noticed is that I always put A in the middle. Now, it's very important that you put this common origin in the middle of your naming for your angle, right? Your middle, this origin, the common origin, there's a special name for it. We call it a vertex. Right? Now, we put the vertex in the middle. Now, yeah, so if we have this is when we're talking about these rays, right? But it doesn't actually have to be rays. In fact, we could have just segments. So CA is now AC is now no longer a ray, but rather it's a segment. Same as AB. AB is no longer a ray, it is now a segment. This here still is an angle, right? Now, what if instead of being a one-sided angle, like a single angle, right? What if we had two lines that intersected, right? So we have A right in the middle, B, C, D, and E. Now there's no way for us to write angle A, because if we write angle A, we don't know what angle we're referring to. Let's see. James, I think we ended off at you with being the next person. Can you name a couple angles that are here? Just like maybe one or two. Like angles here, like EAB, for example, angle EAB. So angle EAB would refer to this angle right here, right? So any other angles? So James says angle DAB. So that would be this angle here and EAC. So those are angles, yes. They weren't really the angles I was expecting you to give me, but they are angles. Okay, we're going to talk more about angles like this, where they pretty much make up a straight line. We're going to talk more about that in the next section. But yes, another example would be angle CAB, which would be this one right here. All right. Any questions about naming these angles here from anyone? Okay, looks like we're good here. So with that, we actually move on into our third section here. Well, another section. And this talks about measuring angles. Now, is everyone here familiar with how to use a protractor? Because a big part of this talks about how to use a protractor. And it's a little hard to show how to use a protractor if I can't, like if I don't have like an on-screen layover or anything like that. Is there anyone here, instead of having everyone who does know say, is anyone unfamiliar with using a protractor? Either just let me know now or send me a message, because if no one speaks up about not knowing, I'm just going to go ahead and skip over this part. All right, so everyone's familiar with using a protractor. Okay, so with that, let's just kind of go ahead and skip over this and move straight on into some of these questions, right? So question 2.1 just has you kind of using that protractor, but 2.2 here is a little bit different. So one of the things that you learn about a circle is that a full circle has 360 degrees in that circle. Now, why is it that we use 360 degrees? Now, if we take a look at these examples here, we can see that in this first example, we see that AOB takes up a fourth of that 360 degree. Isabella, you answered a question already. So Gracie, for angle AOB here, what is that angle measurement going to be?
90.
90, right? So we just take that 360 divide by 4 gives us 90 degrees. And for COD, if COD cuts off a third of that, Gracie again, what is that going to be?
120.
Right. And if we continue going on, we have EOF at 30 degrees and GOH at 1/8 for a total of 45 degrees. Now, the reason why we use 360 degrees is because 360 degrees is a nice number to work with. That's really it. There's no other reason why we use 360 degrees. It's very, what's it called? It's very divisible by a lot of numbers. Now, sure, maybe it had to do with some ancient civilization using a number system with how many digits, but why do we continue to use that number, right? Like think about these numbers here. 360 is divisible by, well, 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, like many of the first 10 numbers, only a single, like 1, like it's divisible by 9 as well, right? Only 7 is undivisible. And then once you move to 15, only 11 and 13, as well as 14, because it's not divisible by 7 either. But like, there's just so many of the first numbers are evenly divisible if you use 360, right? That's the reason why we use 360. That's really it. No other reason at all. But all right. Okay. Moving on. So here we have a couple things, right? So in this first question, if angle WOY is equal to 60 degrees and WOX is equal to 20, Carrie, what is angle XOY? What is the measurement of that angle? Carrie, you there? Not hearing anything from you. Are you sure your mic works? Okay, if your mic's broken, just go ahead and use the chat. So what's the measurement of angle XOY here? 40 degrees. So how did you get that 40 degrees? 60 minus 20, right? So what we see here is that WOY refers to this bigger angle here, right? That's the 60. And WOX refers to this angle here. Now what we can see is that WOX and XOY are two angles that share what we call this ray, right? The rays that make up an angle are what we call sides. So they share a side here in OX. Well, if two angles share a side, we call these adjacent angles. And what's important about adjacent angles is that they add up to create a bigger angle. So in this case, what we know is that WOX, angle WOX, plus angle XOY is equal to angle WOY. So if we go from here, we subtract WOX from both sides. That's how we get that 60 minus 20 to get us angle XOY is equal to 40 degrees. All right, thank you, Carrie. This process, this equation that we created, right, where we had those two adjacent angles, this is what we call the angle addition postulate. And again, we see this word postulate. That means that there's no way for us to prove this. We cannot prove that this is the case for angle addition. We just have to accept it as a fact. All right, moving on, question number 2.4, Brendan. So as we can see here, angle PQR is 40 degrees, but if we go to long way, what is that measurement going to be, Brendan?
Not sure.
You're not sure? Okay, so what do we know about this drawing, right? So what we can see here is that this looks like it's the part of the whole circle, right? So what do we know about that full circle, Brendan?
A full circle is 360 degrees, right?
Yeah, so if the full circle is 360 degrees, we've taken a chunk out of it, right?
Wait, so would it be 320? Because
yeah, exactly.
yeah.
Because what you're doing is 360 degrees, that full circle, and we subtract the 40 degrees that we're no longer counting, right? So what you notice about an angle is that every angle is just a part of a full circle. If you take the angle plus the rest of it back here, you create the full circle, right? So that's what we're thinking about here. Now, this long way around, we just take that 360 degrees, subtract off the 40 to get that 320. And what we call this kind of angle, this long way around, this measurement is greater than 180 degrees, right? So we call these reflex angles. Angles that are greater than 180 degrees. This isn't actually very common. We're not going to be talking about this very much. It's not something that is usually used. So yeah, we're not going to worry about it too much. And lastly, Allison, now I know here we're talking about a protractor to create a 37 degree and a 143 degree angle, which we don't really have, we don't really need. We're not going to do that. But rather 37 and 143. Do you notice anything about these two angles if we add them up together? Like what happens here?
They equal something divisible by 10.
Well, that too, but what's the actual
180.
180, right? So 180 degrees. Now, 180 degrees, the importance of this 180 is that it's actually exactly half of 360 degrees, right? So 360 degrees divided by 2 is equal to this 180 degrees. And what's important about 180 degrees? Do you actually already know this?
No.
So let's think about that diameter, right? Let's bring it all the way back. Run it back. So if we have a diameter for this circle, right? So this, it's that better? That's better. So if we take this line right here, look at this. Let's use another color. Let's look at these 3 points. Let's call them A, B, and C. So Allison, what I've drawn here, AC is a straight line. Would you agree?
Yeah.
It's straight enough. Well, what about angle ABC? What do you know about angle ABC? It
It's
looks
straight.
like, yeah, it's a
180?
straight line. It's a straight 180 degree line, right? So a straight angle is going to be the measurement of a straight line. If you put a vertex here on a straight line, this is going to be 180 degrees. And the reason why that is the case is it because it takes the circle, the full 360 degrees of the circle, and it cuts it right in half. So now you're looking at 180 degrees only. Now, with that, that's actually the end of this section as well. We're going to call it a day here because there's not really much else that we would have time to talk about. So we'll talk about the remaining part of chapter 2, hopefully next week. But I do know that I can say that the next 2, I wouldn't be surprised if we take the next 2 classes to talk about it because chapter 2 is a little bit long. So with that, we'll call it a day for here. Homework is going to be sections 2.2 and 1.2 and 1.3. There's going to be a couple of questions in the exercises at the end of each section. So that's going to be the homework for this week. And unless you all have any questions, you're all free to go.
Is there a Padlet or no?
So I think from what I know, we have a WeChat group and I think we have a Padlet set up. But I'm not the one putting stuff on it. I just know that I think there is a Padlet though. Yeah, 2.2, 1.2, and 1.3 for homework. Yeah, see ya.
I have a question.
Go for it.
Is it like the whole section, or we only have like to do 3 problems?
Like for example, on here, let me just screen share here. So if you look here, right, you have exercises 1.3.1, 1.3.2, 1.3.3. Like all of these questions are homework. But there's only like
Okay.
4 here, 4 in 2.2, and then maybe like 2 in chapter. There's like 2 in chapter 2.2, and then 4 in each 1.2 and 1.3. So there's not that many.
Okay, I thought it was only like 3 problems, which was
Nah,
I was kind of concerned.
nah, you're good. Anything else?
Thank you.
No problem. Well, in that case, have a good week and see you all next week.
Thank you.
Yeah, no problem.